Hello students, good morning. And in the previous video we did the revision of the chapter and we'll continue that revision along with the few numericals that I gave you. So in the previous video we stopped till the parallel resistance, and now we will continue with the next topic, that is the electric power. Okay, so electric power, it is based on the same thing, that is the power of an object that we studied last year in the 9th standard. That is, power is work done upon time taken, or work done is energy consumed in a certain amount of time. That gives us the power of a machine or an object that is doing certain work. Okay, but this is the power for electricity or electric current, so we will have to convert this in the terms of electricity, and hence it is called electric power. So for that we are simply taking the formula of potential difference. Potential difference states that work done in moving unit charge from one end to the other end of the conductor. So the formula becomes V is equal to W upon Q. This we had already studied in the beginning of the chapter, and we also revised it in the previous video. And hence finding the formula for work done by simply cross multiplication of charges with potential difference. When we cross multiply, we get V into Q is equal to W, or W is equal to V into Q, that is work done. And we use this value of work done and put it in the formula of power. So what we get is power is equal to work done upon time taken, where work done is V into Q upon time taken. And we had also studied the formula and the definition of electric current, that is number of charges flowing in a certain amount of time. So I is equal to Q upon T. So over here in our formula of power, that is V into Q upon T, because they all are in multiplication, we can separate them, and therefore V can be separated and we can multiply Q upon T. But we also know that Q upon T is current, so we replace the value of Q upon T with current I. So our next formula for power becomes P is equal to VI, and this is the formula for electric power. Okay, where power is the potential difference into current. Okay, and the unit of power is watt, as before. Sometimes the question is also asked, what is 1 watt? That question was also asked previously in 9th standard as well. Define 1 watt. So 1 watt is the power of an object if it consumes 1 ampere of current when the potential difference is 1 volt. So we can define it as 1 watt is the power of the object or the machine or a conductor if it consumes 1 ampere of current when the potential difference is 1 volt. You just remember this formula and it will be much more easier to answer the question. Always interpret the formulas in terms of definition, it will be much more easier, or if you know the definition, then formulas will be much more easier to remember. Okay, always remember definitions and formulas, they are related to each other. So don't try to mug it up, try to understand the formulas, and according to it you can understand the definitions, or if you are having difficulty in formulas, understand the definitions and it will be easier for you to understand the formulas. Okay, now this formula for power can also be written in other terms as well. We have P is equal to VI, but if we apply Ohm's law, where V is equal to IR, and then you can substitute the value of potential difference in power as well. So instead of V, we write IR, and this I as it is over here. So what we get, P is equal to I square R. This is another formula for electric power. In the same way, we can also convert the formula in terms of potential difference as well. So again, we take Ohm's law, where V is equal to IR. We find the value of current by taking R on the other side, so it becomes V by R is equal to I. Now we use this value of current once again in the formula of power, that is P is equal to VI. Then it becomes V as it is. Then we are writing value of I as V by R over here, so it becomes P is equal to V square by R, and finally what you get is P is equal to V square by R. Remember, if it is in terms of current, then it is I square R, and if it is in terms of potential difference, then it is V square by R. Okay, it's not V square into R, it is I square into R, and it is V square by R. Don't Don't get confused in this, okay? So don't try to mug up the formulas. Go through the process so it will be much more easier to understand. Okay? Once you understand the electric power, the next topic is similar to it, that is heating effect. So we have already discussed about the examples and many of the objects that get heated up when we are using them. Our day-to-day appliances, they get heat up after a certain amount of time. This is the same thing. So if we are using an object, then we are consuming electric power for a certain amount of time, and when power is consumed for a certain amount of time, energy is released or energy is used. In this case, energy is released, that is heat energy. So power into time becomes heat energy. But if we multiply time on in this side, then time is also multiplied on the other side as well. So P into T becomes H and VIT as it is. So this gives you the formula for H is equal to VIT. Once again we apply the Ohm's law after finding the formula for heat generated, that is H is equal to VIT. Then you apply the Ohm's law and you get two different formulas as well. One of them is Joules law of heating, that is you simply apply Ohm's law, that is V is equal to IR, and substitute the value of V over here in H is equal to VIT. What you get is ultimately IR into I into T. Instead of V we are writing IR, and then we are just writing I into T as it is over here. Now they all are in multiplication, so obviously I into I becomes I square RT. So H is equal to I square RT, and this formula is the formula for Joules law of heating. Remember that. Okay. This formula suggests that heat energy generated in the conductor depends on the square of the current, it depends on the resistance of the conductor, and it depends on the amount of time the current is flowing in that conductor. So it is really very important. H is equal to I square RT. Okay. Now this is the few examples of where heat energy is used in our day-to-day lives. All of these examples, as you can see, the most important one is this one, fuse. So fuse is used as a safety device in our houses for different purposes in order to prevent ourselves from electric shock and fire hazards as well. If the heat energy is too much or more of the voltage, a high voltage that you call it, that can cause fire dangers in your home. And how it works is, it is a wire which is connected in your house through this main circuit and supply, and when more current passes through it, instead of the required current, let's say 1.5 amperes is the required current, but more current flows through it, then what happens is this wire melts over here, okay, because its maximum capacity is 1 ampere, so 1.5 ampere of current is flowing through it, which is more than the required current. Then the 1 ampere fuse will melt, and thus it will break the circuit, preventing current to flow in the circuits and help us in preventing fire hazards, and more importantly, it prevents our devices from getting burnt, which can cause us with a lot of trouble. Okay, so this is heating effect of electric current. Moving on, I gave you a few examples related to this, and that is what we are going to solve today. Okay, so the first one is heat energy of 320 joules is generated in 10 seconds across the resistance of 2 ohms. Find the current flowing through the circuit. So I gave you a hint, that is the formula. So H is equal to I square RT. This formula is what you are going to use. Quite simple. Okay, heat energy is given, that is 320 joules. Current I, okay, that is what we need to find. Resistance, that is given as 2 ohms, and time is given as 10 seconds. So you have all the values, all you need to do is find the current. 2 into 10 becomes 20, and cross multiplication 320 by 20 gives you I square. Simple. Remove the zeros. 2 ones 2 and 2 6 12. So what you get ultimately is 16 is equal to I square, or I can write I square is equal to 16. but we don't want the square of the current. Simple, take the square root. Therefore I is equal to square root of 16 is 4. So 4 amperes of current flows through the circuit. It is quite simple. I hope it is clear to you, students. The next one is quite longer and a little bit complicated, not much. So you have a circuit. You have been given 3 resistors, 2, 5 and 10 ohms. The potential difference is 12 volts and it is asked, find the total effective resistance. Well, that is quite simple. Find the total resistance. Because they all are in parallel, we are going to apply the formula, that is 1 upon R parallel. 1 upon R1, that is 2, 1 upon R2, that is 5, and 1 upon R3, that is 10. From this simple equation, you can see that the LCM is 10. You can simply multiply 2 5s and 5 2s. What you get is 5 1 2s is 2 plus 1 upon LCM is 10. So ultimately what you get over here is 5 plus 2 7 plus 1 8. So what you get is 8 upon 10. So what you get is ultimately 8 upon 10. This is 1 upon parallel resistance. Remember, I always taught you that if you are finding parallel resistance, take the reciprocal. This is not your final answer. So the total parallel resistance is 10 upon 8. 8 upon 10, you do the reciprocal, it becomes 10 upon 8. Okay? After solving this, what you get is 8 1s 8. 2 is remaining, so 8 2s 16, 4 is remaining, and 8 5s 40. So what you get is ultimately 1.25 ohms. So the total resistance of the circuit is 1.25 ohms. It is quite simple. The next is the total current. Okay, but before that, the third question is current through each resistors. Now it will be much more easier to find the current through each resistor and then finding the total current. Okay, how I will tell you. First, finding the current through each resistor. Because the potential difference is same, you don't need to apply the total resistance. Just apply individual resistances along with the potential difference. So what you get is V is equal to I1 R1. Okay, and V is equal to I2 R2, and V is equal to I3 R3. You need to find I1, so I1 becomes V by R1. Remember Ohm's law and parallel resistance, this is the same thing. I2 is equal to V by R2 and I3 is equal to V by R3. Simply apply the values. V is 10, R1 is 2, so 2 5's answer is 5 amperes. And the first one answer is 5 amperes. And the second one, V is once again 10, R is now 5, so we write 5, and 5 2's 10, so it becomes 2 ampere. In third one, the resistance is 10, so 10 by 10, answer is 1, so 1 ampere. As you can see, you have individually found all the resistance of each and every resistor. Okay, individual current for each and every resistance. Okay, so the third question has been solved. So through R1 we have 5 amperes, through R2 we have 2 amperes, now R3 we have 1 ampere. So we have found the individual current flowing through each resistors. Now finding the total current. So you simply add. We remember total current I in parallel is I1 plus I2 plus I3, that is 5 amperes plus 2 plus 1, that will give you 10 amperes. Get it? So this is how you are supposed to solve the numericals for parallel resistances and heat energy. I hope it is clear to you, students. Let us recap what we studied today. Okay, so in this video we talked about heating effect. We did the revision. Okay, H is equal to VIT, H is equal to I square RT, and before that we talked about power, that is P is equal to VI, then P is equal to I square R, and P is equal to V square by r, this one. P is equal to I square r and P is equal to V square by r. I hope it is clear to you, students. We'll talk about some more numericals in the next video. Okay? Have a great day.